So for this lesson, we're going to go ahead and work through the next section, chapter 4, and that's working on inverse variations. So a little background. Earlier we studied linear equations, and a linear equation, the basic form of it is that it can be listed as y equals kx. Now I could use m there like we have been used before for slope, but for this we're using k as what's called the constant. Okay, k is the constant of variation. And what that means is that on a direct variation like this, as x's go up in this version, then the y's are going to go up also. It's just a line that goes right through the origin for a direct variation. So these are usually things that are related where one increases, the other one increases. For an inverse variation, it's going to work the inverse way. As one increases, we're going to look at one that decreases on it. So the form for the basics for inverse variation, the first form that we list this in is that y equals k over x, not times x like this one, but over x. So x is in the denominator now. Another way to write this is if you multiply both sides by x on this to get the x out of the denominator. The other form will oftentimes write it as that the k equals the two numbers multiplied. If you multiply x, it's x times y equals the k. All right, so the constant of variation here is the k in both of these, okay? All right, now the graph of this is going to look different. This is going to be a graph that you haven't seen before. It's called a hyperbola, and the idea behind a hyperbola is that its graph is going to go in, it's going to go down in this quadrant down here. So notice as x is increasing, the y's are decreasing. And then over here, as x increases here, the y's decrease as well. It's a curve in both of these quadrants for the basic graph of the inverse variation problem. Now, I want you to notice what's missing from this graph is that there is no value of 0 in for it because you cannot divide by 0. So we can't have 0 for x here, okay? So just as a reminder, when you look at these, 0 is not an option for our domain. So our domain is no longer going to be all real numbers. We're going to have to start restricting the domain for that. All right, so a couple examples of what this could look like. One example is we just write y equals 50 over x. Okay, that would be an example of in this form of what the inverse variation would look like. Okay, if we graph that, if you graph it on your graphing calculator, you'll see this hyperbola look to it. Another way, if we multiply this by x on both sides, you'll get 50 equal to x times y. So an example might be if x is 2, y would have to be 25. So 2 times 25 would give you that constant of 50. Okay, so what we say, because it's an inverse variation, y varies inversely as x goes up, y goes down. Okay, so that's kind of the idea that you have to get from looking at these. All right, let's use those basics and do some examples here. So a couple problems to do. So we'll just use these formulas. Find the constant of variation, x equals 18 when y equals 12. We're going to, the way we phrase this is, we're going to say x varies inversely with y. Okay, so we're going to state that it's an inverse variation with that phrase. X varies inversely as y. So when it says find the constant of variation, I'm gonna use this version here. This version of the two. There's two forms to use. If I just want the constant, my constant is gonna equal x times y. So all I have to do is multiply 18 times 12, all right? So 18 times 12, you gonna do that for me, Andy?
216.
216, okay? So we get a constant of 216 for that. That's all you have to do. Multiply the two numbers, you get the constant. Now this one over here, when we do this problem, if x equals 4 when y equals 15, find x when y equals 10. When you do this, let's find the constant first. So constant equals 4 times 15. 4 times 15 is equal to 60. So that's now my constant. Now I'm going to use that constant to find x. So I'm going to use constant equals x times y. I now know my constant is 60. I'm trying to find the x. I'm going to put in then a y of 10. And now you just divide both sides by 10 and you get x equal to 6. So you just put the values in and get your solutions for what it's asking you for. Okay, now here's the other types of problems you're going to be asked. It's going to ask you, is it an inverse variation? And it might give you a table like this, and what we have to do is test it to see if it is. If it's an inverse variation, then if you multiply the two numbers, you always will get the same. So notice if I multiply 1 times 80, I get a constant of 80. If I multiply 2 times 40, I also get 80. If I multiply 4 times 20, I still get 80. And then 5 times 16, I get 80. You get the same constant every time. If that's the case, the same constant, you're going to get, this is going to be yes, it is an inverse variation. You try it with this one. See if you can multiply these together and see if it's a constant. Okay, so try it with each one of these and see, does it give you the same constant? What did you get for a constant for the first one? 100, right? Okay. What'd you get for a constant for the second one?
Not 100.
Not 100? Okay, that's a good answer. Right, what's 15 times 30? Is that 450?
Yeah.
Okay, 450. As soon as you get that one of them doesn't match, you don't have to keep going. You just have to say, no, those are not the same constants. So no, those are not matching for that. Right? Any questions on this before I move on? I will take questions at this point. All right, let's go to the graphs now. So those are not hard. You just have to remember that idea that we're working with. Multiplying the two numbers together to get that constant is the primary way we use it. Now with graphing, what we're going to do is we're going to expand out the inverse variation, and these are going to be graphing ones that have denominators. And what you have to remember when you have these denominators, okay, here's an important idea. You cannot have 0 in the denominator. Now we've already done asymptotes and talked about this. Okay, what I want you to make sure you do is recognize that we're going to have asymptotes with these because we have the case where the denominator might equal 0. So what you look at here is you're going to, first of all, have an asymptote is a line that the graph, gets close to but does not cross. And I'm going to put in parentheses, we're gonna make it a dotted line. Okay, so there's gonna be vertical and horizontal asymptotes for this. Now for this graph here with x minus h, okay, I'm gonna at h, I'm gonna put h right here, okay, a value, it's like if that were x minus 4, this would be a 4. Make a vertical dotted line there, that's an asymptote. Okay, vertical asymptote at h. This k is gonna be at my horizontal asymptote. And so for this, I'm gonna go up to k here, I'll put k right there, and draw a horizontal asymptote. So those are values that we're not gonna actually get to, we're gonna get close to on the graph. Now you might ask, well this one's the opposite, because we're doing the opposite with that negative, this one's the same. It's as if this k were over with the y. If you think of it as y minus k equals a times x minus h, this is kind of like our constant of variation. And over here, when it's with the y, that k is the opposite, if we put it with there. And the graph would look like this. You're gonna draw that just like we did on the other side with our graph. You're gonna draw this hyperbola that goes in both quadrants here. Okay? So our vertical asymptotes, okay, this is from the denominator. Okay, this is where x does not equal h in this example. Okay, this relates to the domain. And the denominator. Whereas the horizontal asymptotes, the ones that we draw horizontally, this is where y does not equal k. This has to do with the range. We have kind of missing range values from this. All right, that's a lot of theory. Let's go ahead and do now an example with each of these graphs, okay? These are gonna be fairly quick and not necessarily very difficult to do. You're gonna use your graphing calculator at times. So we wanna do y equals 3 over x, and we're gonna state the domain and range, okay? So I'm gonna put this in on my calculator right now, okay, just to show you what it looks like. So we're gonna clear out what was there. We're gonna put 3 divided by x, and I'm gonna hit zoom and my standard graph. So notice I've got that hyperbola look here. It goes like this and like this, okay? Now, where are those asymptotes at? Well, there's no numbers here like we had above, so your asymptotes here are gonna be at x equals 0. So our vertical asymptote has to do with the denominator. X cannot equal 0 because there's nothing there with it, so we just say x can't equal 0. There's nothing out here listed for the horizontal, so the horizontal asymptote is that y cannot equal 0. So my graph, and we can get a couple values off the table. So second table here. Okay, I'm gonna have 1 with 3, 3 with 1, and then a bunch of other decimals. So 1 goes with 3, 3 goes with 1. Also I had 0.5 with 6, and 6 with 0.5. And so what we get for a graph now is we get this coming down like this. Then we're going to do the ones over in this quadrant down here. We get -1 with -3, and -3 with -1 off the table, -6 with -0.5, and -0.5 with -6. Okay, those are all off of the table here, like 6.5, 3 with 1. Just have to plot some points off of your table. And then so we get our graph looks like this. See that hyperbola look to it. All right, so now let's go on to, and so that would be make our domain, folks, this is new now. Domain used to be all real numbers. It's gonna be all real numbers here except 0. Okay, and our range is gonna be all real numbers except for 0. Okay? All right, let's do this last one here. On this one, when you look at this, your denominator gives you your vertical asymptote. Your number out here gives you your horizontal asymptote. So my vertical asymptote is going to be at x equals 4. What would make that equal to 0 there? So we're going to go out to 4 here and create a vertical asymptote, a dotted line. Okay, and my horizontal asymptote will be at x equals 5. So notice it's the opposite of the denominator, but it's the same as the numerator. So go up here to 5 and draw an asymptote here. And so that will determine my domain and range. So without even looking at the graph on the graphing calculator, my domain is just going to be x cannot equal 4, and my range is that y cannot equal 5. Let's change that to a y. So this should be y equals 5 is my horizontal. Okay, see that? I did an x there. It should be a y equals 5. All right, let's put the graph on the calculator. Let's enter this in. So we're going to put in for y equals, clear this off. We'll do 1 divided by x minus 4. So I'm going to put x minus 4 in parentheses, x minus 4. And then outside of that, I'm going to put a plus 5. And so when I draw my graph, looks like I have a syntax error. Let's go ahead and, I have a double plus there. Let's delete one of those off. So looking at my graph, here's the graph goes like this and like this, okay, on it. And looking at the table, you can get some values just to get it started. So I'm going to go with 3 with 4, 2 with 4.5. So 3 goes with 4. So 1, 2, 3, 4. And then I'm going to have 2 with 4.5. And this graph is going to go like this, kind of tight onto it here. And then the mirror values over here will give me a graph over like this, using those table values. So these are hyperbolas, and they come from these graphs when we have denominators that include the variable. They're based on inverse variations, but these rational expressions will give us graphs that include asymptotes.